Hi everyone, we continue our discussion some of integrated optical components, continuing also the same thing, directional coupler. Today we will be discussing about some design aspects and how we can go for modeling the structure directional coupler, so that it can be useful for a circuit simulation. So, first thing what I will do, we have derived coupled equation for coupled waveguides, differential equation, and we know how to solve analytically with some approximation, and we found that this kappa is the major factor which we need to know for a coupled waveguide structure, so that we can use those in analytical solutions. So, we will discuss today how one can extract this coupling coefficient from some numerical calculations, so that you can use in analytical formula. And then we will be discussing about some kind of design of practical directional couplers. So, you have to go for designing such that it can be fabricated compatible to the technology, and also you should get some your desired specifications you want. So, anything you design, that should be possible to fabricate in the foundry or in the fab, in the lab, laboratory, university labs, etc. You should be able to fabricate. Okay. So, third thing I will be just discussing, I will just briefly I will be showcasing some device architectures that can be demonstrated, that can be designed using a directional coupler, using one directional coupler or combination of directional couplers. So, that is why it is DCs. DC means directional coupler, here we are meaning. So, let us start with a simple structure that we have a this is our directional coupler, this is input waveguide, input output, you can consider this one input optical input and optical output here we can consider, and we can just launch from these two ports A0, B0, and then in the output we can get A1, B1, and we maintain a distance between parallel coupled waveguides in the central region of length L with a separation of S. So, in that case we know the transfer matrix form we can write. If we are launching with a amplitude a mode with amplitude A0 and B0 are the inputs, and then in the output A1, B1 we can find out in case of identical waveguide structure. Both these waveguides are identical. If this is beta, also this is also propagation constant beta is giving, then waveguide width, dimension, everything they all respect they are identical, then we can simplify our transfer function with cos kappa L, that is kappa whatever coupling constant we are talking about, and then this is actually another things which is cross coupling part, and normally we call this one as a R, we represent this one as R and this one as T, and then this will be minus JT, this will be minus JT, and this would be minus JT star, and this should be R star. Okay. So, the unitary matrix comes like the determinant of this matrix will become R square plus T square, and normally if it is lossless, normally you know this reflection and transmission. So, anything going back we call this as a reflection, and anything coming back transmission. Sometimes it is mentioned like this is R and this is K, some textbook you will find that whatever the value it is cross coupling, that is actually K value you are considering. Okay. So, if we just represent this one R and this one T, then we can reduce in a very simple transfer matrix of a directional coupler R minus JT star R star. So, that is what we have already discussed in the previous lecture. Now, if we want to design this directional coupler so that you get a 3 dB coupler, that means if you are launching here 1 watt, then you would be getting 0.5 watt here and 0.5 watt here, then it is called 3 dB power splitter. 50-50 splitting is 3 dB power splitter. So, in that case we have to design kappa and L such that this R equal to so called cosine kappa L, that if it is somehow giving you 1 by root 2, then what happen? We can get here A1 also you will be getting something like that, whatever A naught it is. If you are not launching here anything, if A naught is launched, then A1 will be A naught by root 2 and B1 will be also A naught by root 2. Okay. So, in that case total power will be here A naught square by 2 and A naught square by 2. If you add them, then it will be A naught square, which is your input. So, then it is accordingly, if you design your transfer matrix, that is R equal to 1 by root 2, T equal to 1. So, 1 by root 2, 1 by root 2, if you take a factor, then you can represent 3 dB power splitter using a directional coupler. This would be your transfer matrix. Okay. Fine. So, now let us clean up things. For example, we can write this. Suppose for a given directional coupler, the separation everything is there and some constant S value is there, and if they are maintaining a certain distance and uniform, that means kappa should be a parameter for this entire structure, that is a constant, that is a specification figure of merit of this structure. Okay. So, only thing is that if I maintain that waveguide dimensions, then just controlling the length alone, you can control how much power you are launching in the cross port. If you are launching here, let us consider B naught is nothing is there. So, how much power you will be getting in the bar port, and this will be in the cross port. B1 is the cross port, and if you, with respect to this input, this is your bar port, and with respect to this will be your cross port. If you are launching here with respect to this one, this will be your bar port and this would be your cross port, that is vice versa. Okay. So, if kappa is known and fixed, some kappa value known is known some way, we need to extract that value of course. If kappa known, then I can just find a value of L length exactly pi by 4 kappa. So, if L equal to pi by 4 kappa, that means cos kappa times pi by 4 kappa, right. This L value, this is your L value. So, this kappa cancel, then pi by 4, cos pi by 4 it will give 1 by root 2. So, that is how 1 by root 2 you will be getting. A1 will be A naught by root 2, B1 will be A naught by root 2, that is what we have discussed. Okay. So, I can say that if a directional coupler, some kappa value is known given to you, then you can easily model that if I need 3 dB power splitting, then my length will be just exactly pi by 4 kappa. You know kappa, the dimension of kappa is per micrometer, per millimeter, per meter or whatever. So, accordingly L3 dB it is a length, L3 dB you can find out. So, kappa value depends. So, higher the kappa value, you can make compact 3 dB power splitter. Stronger kappa value is welcome to design a compact footprint, smaller device structure. Okay. But stronger kappa can cause a lot of other issues also. It can introduce some kind of radiation, scattering losses, all those type of things will be there. So, you have to be careful that while increasing kappa, you should not add some additional losses in the structure because of the structural non-uniformity and so on. Okay. Now, we know given kappa, I can design length for 3 dB coupling. Now, let us come back to our original cross section structure. Suppose if you take a cross section here, this is top view, cross section here, you have a one waveguide, another waveguide, their separation is S given here, okay, and you know that is this delta NB square is actually presence of second waveguide, delta NA square this represent presence of the first waveguide, and this is your slab height. So, if you just consider NS and then slab and then NC, together it is a background, and only additional part this one actually giving you waveguide B and this one gives you waveguide A. If you are missing, if you are removing that one, that means you have only waveguide B, and if you are removing this one, then you have waveguide A. So, delta N square, delta NB square, just that additional in the ambience, total ambience, additional refractive index, additional material property you want to include, so that you can get some kind of waveguide structure there. And we have assumed that this type of transfer matrix we have derived when we consider that beta A equal to beta B equal to beta. That means identical waveguide structure. If it is non-identical, then we need some additional term would come here, that is actually delta equal to beta A plus kappa AA minus beta B plus kappa BB we have derived earlier, this should be 2 delta. Okay. Now, since it is identical, we have in the coupled equation, you remember that we have introduced kappa AA, that should be kappa BB, and that will be actually delta beta, and that expression will be like this, that is derived using coupled equation in the last lecture, and kappa AB, kappa BA star, that is actually kappa, that actual contributes the coupling constant, so called thing. So, one thing is clear, that this kappa expression, that once you know electric field profile, dominant electric field profile of waveguide A and waveguide B, and what is the additional delta n B square you are n A square or n B square you use here, then if you integrate, then you will be able to get kappa. You can just simply calculate your kappa value by solving the mode profile, mode field distribution independently of individual waveguides. And if you just introduce and then integration, that is one way of calculating kappa. However, you know, sometimes each time different type of structure, you may not need all the time this type of calculation, this type of solution, it would be very difficult time to time. So, we need some kind of alternative approach to extract kappa value. With our knowledge so far we discussed, based on that I will be following. Okay. Now, suppose delta beta naught equal to 0 and kappa will be equal to 0. If you just look into this one, this expression, and look into this expression, as long as they are single mode waveguide, electric field distribution for the first waveguide, electric field distribution of the first waveguide, delta n B square, that is the additional refractive index, whatever in the second waveguide, that is your delta beta. When that will be 0? Obviously, when if you just have your structure such that one of them will become 0 at some regions, or if you integrate everywhere, either this one or this one or this one, entire xy plane, you will find one of these 3 will become 0, entire plane, then this delta beta will be 0, and that is only possible when S tends to infinity. Suppose they are, at least infinity means practically it is a very large distance. Okay. If they are separated with a sufficiently larger distance S, maybe for silicon waveguide it can be several micrometer is sufficient, okay, because waveguide dimensions are in some micron level. So, when S tends to infinity, then we can say that delta beta naught will be equal to 0. That means, this propagation constant modification of the first waveguide or second waveguide due to the presence of first waveguide, that will not be that much significant. Similarly, when S is large, then we can say that this kappa coupling strength will be 0 only when S equal to large, because you will get everywhere, because if it is a large distance, either EA will be 0 or EB will be 0 or delta n A square will be 0. If they have some value, delta n A square will be 0. So, in that way you can say that you can ensure that for a large distance one value we are ensuring that both delta beta and kappa will be 0, and that in that case we can say that they are decoupled completely and they maintain their orthogonality condition individually. Okay. So, that is what we learned so far. Now, we will just try to make a simplest model. If you see normally, you know, electric field distribution, if you just see something this direction, if you just plot fundamental mode, it will be almost Gaussian, and if you see that almost it is Gaussian, at infinity it will be 0. So, just following that, the field will be dropping like one edge, if you see it is almost similar to like a exponential term. So, for our compact modeling purpose for the directional coupler, we can say that delta beta and kappa, they must be depends on S. As you increase the obviously, you know, when S tends to infinity, kappa value also 0, delta beta is 0. As you decrease your kappa S value, then kappa will start growing and delta beta also will start growing. So, in that sense, we can model with a analytical expression, empirical, you can say that empirical formula, we can consider delta beta S, S means space dependent, waveguides are identical, we are maintaining that cross sectional refractive index profile, only their S lateral in the along x axis we are just changing. If we change, then we can say that that u is some constant s minus s naught, and kappa will vary, kappa naught e to the power v, u v are positive constant, u v are some positive constant, we are considering positive constants. Okay. And s naught we maintain that, you know, it is clear that smaller the s coupling will be more, but how small you can make, that depends on your technology, because two features all over CMOS technology, whatever device structure you define, you can fabricate using your CMOS foundry, that depends on your technology node. Suppose for example, if you are using technology node of 180 nanometer, then probably this feature, this separation you can maintain with a great yield, good yield, that would be in the order of 150 nanometer or so. If you are going for advanced technology like 45 nanometer, even for 25 nanometer technology, CMOS technology, then probably this gap can be reduced further. So, we maintain that depending on the technology node, S naught is fixed. So, that is the minimum value of S naught is fixed. So, we can define that what would be the maximum delta beta or kappa you can acquire. Actually speaking, this delta beta has no meaning as such for modeling a directional coupler. Kappa is very important, because kappa depending on the kappa you can define what is the length required for 3 dB power splitter or complete power splitting, right. So, I can model like that, as S increasing from S naught, S minus S naught, then this kappa naught will be decreasing exponentially with a constant, some kind of constant V. Beta similarly some constant u, S minus S naught. So, when S equal to S naught, then obviously delta beta will be delta beta naught, kappa will be kappa naught. So, that means at S naught I know what is the constant value, what can be the kappa value I can think of, I can calculate and then I can plot that way. So, we need to know for a given S naught technological things, once you know that kappa naught, then you can just model, if you just increase S, then how it will be varying. Obviously, you need to find some fitting parameter u and v. Okay. So, S naught is the limited by technology node, that is what we can model, right. So, now you see, normally coupled waveguides, we have seen that there are two different type of solutions we can get, symmetric solution and asymmetric solution. So, when z equal to 0 in the propagation direction, when coupled start from here, this is actually z equal to 0 for example, and this is actually z equal to LDC or whatever you can say. At z equal to z naught, if you are not launching anything in the second waveguide, only first waveguide you are launching A naught equal to 1, meaning A naught square you can consider, that is actually 1 watt or so, just normalized A naught equal to 1. Then we know that the symmetric mode and asymmetric mode, their amplitude will be shared by 1 over root 2, 1 over root 2 at z equal to 2 naught. That means 50% of power will go to symmetric mode and 50% power will go to asymmetric mode, antisymmetric mode. Antisymmetric, all these symmetric, antisymmetric solutions we have discussed also in the last lecture. Okay. So, our intention is that how to find out kappa, and so that we can model like this, at least we can find u and v and S naught, so that we can use this formula for any circuit simulation. We will be able to know if the S is we reduce, whether the performance is increasing or decreasing, just with a single parameter you can think of the directional coupler for a given length, or maybe length also, of course. Length will come here actually. Okay. So, this is symmetric and antisymmetric, how they will be coupled, that is it is shown. And when z equal to LC, where we want the length that after travelling power launched in here A naught equal to 1 already at z equal to z naught, okay, and here you have done nothing, nothing is launched here, then at z equal to LC I would see that this mode, symmetric mode, will travel with a phase of 2 pi times integer value m, and suppose at that particular length equal to LC, the asymmetric mode, that will acquire phase of 2m minus 1 pi, pi less, that means their phase difference is exactly pi after travelling LC length, right. So, in that case this one will be flipped here, and if you take a superposition, this negative sign, this positive sign, this in the waveguide A you will see nothing, and symmetric positive, antisymmetric also positive, second waveguide you see the maximum. So, in that case, if I launch A naught equal to 1 here, I will get B naught, B1 equal to 1, A1 will be equal to 0, here nothing will be there. So, that means complete cross coupling takes place. We can explain that just considering symmetric and antisymmetric supermodes, and these supermodes can be actually solved. So, now I will do a trick actually. You see, I can say that beta s minus beta s times LC, that means beta s LC multiply and beta s LC multiply. If you subtract, that means after traveling this LC, this L is smaller LC, I have written here, capital LC here. So, they are same basically. So, if you subtract for that length, then you would get their phase difference is pi, and that is the length you need for cross coupling, right. Now, in another way, from the transfer matrix we know that LC is required pi by 2 kappa, right. Pi by 2 kappa is LC, that is what we have discussed earlier, that is why I am carrying forward just to use now. Here if we just use LC, what happens, then I can express kappa in terms of beta s and beta s. Assuming that this symmetric and antisymmetric modes solutions you can easily calculate. You just give a mode solver, and then you will be getting two modes, and you can find what is their eigenvalues, propagation constant for symmetric and antisymmetric mode. Once you know that symmetric and antisymmetric mode, using this two equation you can find kappa value. Okay. Here LC is there, here LC equal to pi by beta s minus beta s. So, this and this if you just make equal, then I can get kappa equal to say whatever the value comes, you just I have just written here, just use this one, then kappa will be, you just compare this to, use this LC here, and then this value, you know, beta equal to 2 pi by lambda n effective s, beta s equal to 2 pi by lambda n effective asymmetric, and this 2 because you have 2 here, 2 kappa, LC if you are putting here pi by 2 kappa, right, and whatever 2 comes, 2 to cancel, right. So, pi both sides will cancel also, then you will be getting kappa value is this one. So, where kappa value can be expressed in terms of, if you know the effective index of the symmetric and asymmetric mode, obviously symmetric mode is the fundamental mode for the combined structure, asymmetric mode is the first order mode for the combined structure. They can be easily solved using a mode solver, commercial available, or you can develop yourself as discussed in our early lectures. So, once you get this thing, then you can find this kappa value. This kappa value can be easily fitted with this expression, so that this expression can be useful for your analytical or for your compact model. Okay. So, here you see basically if you know the refractive index, effective refractive index change between difference between symmetric and antisymmetric mode, then if you know the what is the operating wavelength, suppose 1550 nanometer, and if you know delta n, then you know what is the value of kappa. Once you know kappa value, then you can use, depending on the length, you can use this transfer matrix, then you can find what is the ratio power or amplitude in the cross port and bar port. A1 is in the bar port or B1 is the cross port. So, we can find out. So, main thing now is that this kappa, instead of solving numerical things where delta and b is there, you have to define this little bit of program you have to do. Instead of that, you ask your mode solver, give me the solution for this structure, what is the symmetric mode and asymmetric field distribution, and mainly I am interested to know what is their eigenvalue, that means beta s value and beta s value. Once we know that, I can extract for a given lambda what is the effective index and then what is the kappa value. So, this is the one easiest way we can find, we can use. Now, here it is, here we go. We have used a waveguide dimension of 500 nanometer, device layer thickness of h equal to 220 nanometer, and then small slab area, slab we have considered 0, that means completely etching photonic wear, and gap if, as I mentioned, that in 180 nanometer technology one can easily fabricate 150 nanometer separation between two waveguides. So, here is the cross section, this square, this rectangle, if you see, that is actually 500 nanometer by 220 nanometer. The aspect ratio is different, that is why it is looking like a square, but it is not really square, it is rectangular dimension. This one also rectangular, this one also will be rectangular, because 500 by 220 nanometer. Now, if you solve for T mode, that means you are solving for EX component, okay, dominant component. That EX component, if you solve, then you can see your electric field distribution will be looking like this. Okay. So, in the center it will maximum, the maximum will be 1. So, it is, we have already shown that this symmetric mode will be looking like this. So, one hump, another hump. So, this is your symmetric mode you are getting. One hump maximum in one first waveguide, another hump will be in the second waveguide. So, this is symmetric mode, that is mode solver giving. And then go for higher order mode, then you will see again you will be getting, suppose something like this you are getting, right. So, this type of mode you are getting. This side is negative values, you see -1 color, this is the color code. This one is -1 and this one is +1 red, here +1. So, it will be if you are just giving the field strength, then if you are just doing like that, this will be +1 and this will be -1. So, that means you are getting something like this type of mode. So, you know what is the mode solution, the field distribution giving to you. It can be, it is giving you maybe dominant component of the electric field. At the same time, mode solver will give you what is the beta effective index for the symmetric mode and what is the effective index of the asymmetric mode. You see, symmetric mode is 2.4623 and anti-symmetric mode is 2.4298. So, that means this is lower. So, that means it is sure that beta S is greater than beta AS. You know, beta value is nothing but 2 pi by lambda times n effective, right. If it is S, it is S, we will call it S. If it is AS, we will call AS, that is it. So, now I know n effective value symmetric and n effective value asymmetric. So, I can easily find out what is the delta n value, there is difference. Once you know the difference and lambda we are calculating at 1550 nanometer, put down lambda value. Okay. Then I can find kappa if lambda is in micrometer. For example, in this case delta n equal to, say, let me write down 2.4623, 2.4298. So, if you subtract that, whatever the value you will be getting 5 and this will be 2 and then this will be your 3, right. This will be 3 and this will be 0. So, 0.03, for example 0.0325 is the delta n. So, that means kappa value will be, I can easily calculate, kappa will be pi times 0.03 divided by 1.55 micrometer. So, that will be then micrometer per micrometer value will be getting, right. So, 0.03. So, you can get this cancel 155. So, something whatever value comes micrometer you can multiply some 100. So, that is the kappa value. Depending on that kappa value you can find out what is the length required for a certain power splitting ratio. So, this is what we have calculated. One of our student actually helped us to calculate this thing. Mostly any commercial software mode solver nowadays available, you can use them, you can solve easily. Okay. Otherwise, you can develop your own code as we have discussed in the early lectures how to develop. And then what we discuss? We tried to find out, as I say that, as I predicted earlier, that if you just change the gap S, increase the gap, delta n value will be dropping, because symmetric antisymmetric mode they will be slowly will lose their coupled nature, superposition nature, as if they will be like a independent identity. So, delta n, that is their separation, that is symmetric and antisymmetric mode, they will be propagating with the same phase velocity. So, almost 0 it is going when their S is very large. For example, here we are considering 1000 nanometer, meaning 1 micrometer. If this separation is just 1 micrometer, you will see that they are almost decoupled. Just 1 micrometer. Now, you bring down and you are getting the 150 nanometer here. Then you get, as I calculated, 0.32 or something like that, exactly you are getting here also 0.03. And something very sharply falling, exponentially looking like, and coming there. So, from here you can calculate kappa, because kappa is, once you know delta n, you just insert delta n for every s value, you can get a kappa. It is just something we consider here, whatever value you will be getting here, delta, say we can consider kappa naught e to the power minus b s minus s naught. So, s naught is 150 nanometer, that is the value. So, as you increase s value beyond 150 nanometer, and kappa naught will be this one, about 0.065 kappa value, whatever calculate per micrometer of course. Okay. If it is 0.06 per micrometer, then per millimeter will be, it is 65 probably, yeah, 0.065 for example per micrometer. So, per millimeter will be 65 per millimeter. Okay. And you can consider per centimeter, means it is about again you have to multiply 10. So, then it will be 650 per centimeter. Okay. That way you can keep on calculating, as you will go for longer length, that value will be, and it is obviously exponential decay. You can fit with this data, simulated data, and you can get the parameter v. For example, you can fit, this v is a fitting parameter. Once you get a fitting parameter, then I can say that okay, this is my analytical formula, numerical, semi empirical, you can say that we can use that for circuit simulation. So, this is one type of way how to extract kappa and how to model in this form, right, delta beta naught if you need it. Obviously, this delta beta naught is needed because if waveguides propagates here, you know what is the length, but you need to know what is the propagation constant, so that after traveling this much, how much additional, because of the path, travel path, how much phase it will be acquire, that you need to know by beta. Suppose original beta was beta naught or whatever beta value, then this delta beta naught you have to add, that will be your propagation constant, and if the travel length is L, then you know beta plus delta beta naught times L, that will be the phase for the whatever upper part going here, that phase you have to include, and the lower part also you can consider beta plus delta beta, they are common basically. If they are identical waveguide, this phase acquire whatever power propagating through. When it is decoupling, then you can find out what is the additional phase it acquires here and what is the phase additional it is acquiring here, that you can calculate easily. Okay. Now we will go for some kind of practical design of a of directional couplers. You know, whenever we are just designing like this, you know, this is a simple structure, we just make separation decoupled here and it can bend here. We said that it should be bending, should be adiabatic, so that you do not see any sharp transition, so that light mode can be actually smoothly propagating from one type of waveguide structure to another waveguide structure when their propagation constant is changing, direction of propagation is changing. So, you could get some smooth things. So, that is actually very important, that to make it smooth. But one more important thing is that you cannot just calculate the what is coupling happening in this length and say that this is my model, because you know in the previous slide if you see, as increase the length, it is not that their separation increasing, it is not that their coupling is suddenly coming down to 0, it is not like that. If you are just starting with a critical gap is S naught, then if you see as you go in this direction, their separation is increasing, that is it. But that does not mean in this Y junction type waveguide no coupling is happening. We need to find out what is the coupling happening in this band region, how far they are coupling. So, you have to stretch that much when it is coupling is almost 0, and then you can bend parallel, so that you can access your output things. Okay. So, that is actually important to account what is the coupling happening in this junction region, the transition region also. So, whatever coupling here happening, that is important. In addition to that, you have to consider what is coupling happening when they are slowly adiabatically they are decoupled. Okay. That thing also need to model. Okay. So, for adiabatic transition we can have this type of two directional coupler, they can be made decoupled. Instead of two symmetric separation, you can have one waveguide straight, another waveguide you make a separation, so that it can be decoupled. Okay. So, in that case it will be this separation actually less slow. Here actually separation is abrupt, almost 2 times 2 times separation is happening. This is also moving this side, this is also moving this side. So, separation is it is being separated very fast, and here separation rate is half of that whatever you are getting here. And then you can also think of that instead of taking output in this direction, you can have some device structure output you want to take opposite direction also. So, you can leave like this also. So, these are actually so called directional coupler. So, if you launch light here, how much it will be coupled you can find here. If you launch here, how much it is going there, how much coming here, how much leaving here. If you launch here, how much it is going in the backward direction here and how much it is passing this direction. So, in this way you can design. And while designing that, this bent structure, you cannot really bend very sharply, okay, because you know any sharp bend is not adiabatic. The mode sudden change in k value cannot be actually cannot very easily it can be accepted by a guided mode, because when it is changing k value, you know, while propagation, the propagation constant also need to be maintain some kind of boundary condition. If that is not maintained, that means some kind of loss, some kind of it is actually it will lose some kind of orthogonality condition and light can be scattered into the higher leaky mode. So, in that case bend loss will be there. So, you have to bend that sufficiently large so that bending loss is minimum. For silicon waveguide, this bending loss you can make around 5 micron, 10 micron with some kind of loss. If you are just bending radius is more than 5 micron, 10 micron, maybe 15, 20 micron, I think bend loss is almost adiabatic and no loss is there. So, that way you have to design. I will not discuss that bending related things, but if I get opportunity I will discuss whenever necessary. But for the moment we assume that this bending radius is tolerable. So, that bending loss is minimum. That is what we will assume for this discussion today. Okay. Now, let us take this example of this type of directional coupler, where actually the waveguides are getting decoupled very fast. This is also going that direction and this is coming this direction, and we maintain a coordinate like this. This is your propagation direction z, and top view if you see this is x direction and vertical direction is y, some way we are representing like that. And then we know that here in this region this gap we maintain depending on our so called critical coupling. Sorry, it is limited by the technology node. So, technology node can give you minimum feature of 150 nanometer separation. If you want 200 nanometer, that is also fine, but at here we are just considering, okay, you maintain S0, which is actually you can fabricate in some kind of lab or in the foundry with a good yield. So, when S equal to S0, I can calculate what is the kappa naught, just calculating symmetric and antisymmetric mode, and using this formula I can find kappa naught. S only I will be putting there. While solving asymmetric and antisymmetric mode, S will be just 150 nanometer, or depending on the technology node or the yield you can get in your laboratory, fabrication laboratory. Now, slowly this is going. That means I can't say that no coupling is happening in this region. They are still coupled, as long as their one and tail is interacting each other, they will be still coupling. So, how to calculate that coupling, okay, in the bend region? So, we can just simply say that this kappa here, it is actually S dependent kappa value gap. If it is widening, I know that kappa value will be dropping exponentially, and that exponential formula is like this. And now, the separation is also a function of z now. So, if I just put this S equal to a function of z, you can calculate depending on the bending structure, the math you can do, and then you can find out for a given z, as it is going z increasing, what is the separation between these two waveguide is happening. As you go for further, what is the separation? So, I can get a function separation as a function of z. So, separation at a function of z, and if I just subtract from S0, because when S equal to S0, that is actually here it was S equal to S0, and from then there onward S is increased from S0. Okay. So, I can actually I can model something like this, that whatever value is there, that is a z dependent, I integrate over dz, and I integrate 0 to infinity z in the dz z direction, I can integrate over infinity. You do not need to integrate up to infinity, it can be several micrometer probably, as long whenever it as I have seen that if it is 1 micron separation, then no coupling is there. You can go up to 10 micron separation. that up to that z you can calculate and you can integrate. So, that exponential term dz, and you know that expression is k naught times this one, and if you integrate, then I can say that k naught times whatever integration value you are getting, because this is a number, whatever integration value you will be getting, that we can say that L effective B. So, I can actually model this bent structure as if that is a parallel waveguide with a effective length of this one and having same kappa naught. What is happening, what is the kappa naught in the parallel section. So, practically I have to design like this, but mathematically I can say that this L is now modified into L plus 2 L plus 2 L effective B. That will be actually total directional coupler length, effective length, and I can consider whatever k naught kappa naught I am considering, that will be kappa naught, and then I can say that okay, even though I am showing here it is something, we can assume that the waveguide starting from here, if I just include the length, original length here, then starting from here I can assume that the waveguides are not coupled anymore, because the effect in the coupled region I have just included in the total length, so that I can use this transfer matrix perfectly. Okay. That is how we can say that the actual LDC, what is the L naught in the central portion, whatever L naught will be getting, I can say that this is L naught, and then what is the effect in the bend region equivalent thing and bend region equivalent thing, and that LDC I will be using here in this transfer matrix. If you see, now I am writing kappa naught LDC. LDC, that means bent structure, both side I am bent structure will be there, that I can include in the model. Okay. So, this is straightforward. So, only thing is that you need to know what is the procedure stepwise you have to do, and accordingly you can design your device. So, now let us now see, okay, if you see this kappa value exactly, that is actually kappa naught equal to, that is actually effective index of the symmetric mode, effective index of the asymmetric mode, and also lambda involves. That means this kappa naught is lambda dependent. N effective also, you know that when you calculate effective index, they are also wavelength dependent. This is also wavelength dependent. So, that means kappa itself is a wavelength dependent, right. Now, our intention is that a waveguide designed for one particular wavelength, it may not work, a directional coupler designed for one lambda, it may not work for another lambda. Suppose I want to have a 3 dB power splitter, a certain length. So, certain length it can give 3 dB power splitting at a certain wavelength. Now, if you want to operate same device, if you want to operate in another wavelength, so instead of 1500 you want to use it 1600 nanometer wavelength. So, in that case this kappa is wavelength dependent, that means the directional coupler will not be 3 dB power splitter anymore. So, that is a problem. So, what we do, let us try to see how one can get a wavelength independent directional coupler. That means at least a certain bandwidth it should give you around that wavelength, around maybe 100 nanometer, 200 nanometer wavelength range. You should see that if you change your wavelength for WDM purpose, wavelength division multiplexing purpose, DWDM purpose, suppose I want to use a broadband, all the channels I will be using 1500 to 1600. In that case, around that wavelength I would see this kappa naught is not showing wavelength dependencies. So, how to get that? Let us try to find out d kappa naught by d lambda. You know that if you see this d kappa naught by d lambda, that means as a function of lambda, if you find something, this one is 0, that means kappa naught is constant over lambda. If you just see that d kappa naught by d lambda tends to 0, that means kappa naught will be tends to lambda independent. I have the expression for kappa naught, this one, and if I try to find out d kappa naught by d lambda, kappa naught means for S naught, what is the technology limited gap, that for corresponding to that whatever the kappa naught value. Okay. Now, if I just try to do some kind of differentiation of this one, then I kept with respect to lambda first, pi by minus lambda square and delta n naught lambda kept there, and then I want to do differentiation here pi by lambda d lambda of this one. So, I know at least from our mode solver I will be able to know what is the this difference in effective refractive indices of the symmetric and antisymmetric mode, how that is wavelength dependent. That curve will be able to get from our Moore solver. I will tune lambda and try to find out symmetric mode, antisymmetric mode, what is the effective index for the symmetric, what is the effective index for the asymmetric, and subtract that. That will be the delta n for that particular lambda. Tune lambda another value, tune lambda another value. So, you get a function. So, from that function I will be able to find what is the value like this. So, you just little bit modify minus pi by lambda square, if you just take common, then it will be delta lambda, then minus del d by d lambda. And this type of thing earlier we have discussed, that something you remember, that n effective minus lambda d n effective by d lambda, that is actually nothing but ng, group index. That means, this group index is very important to estimate how information travels through the circuit, okay, because information means modulated signal, several frequencies will be there. So, several frequencies as a group, how they are traveling, that velocity comes from this expression Vg equal to C by Ng. Okay. So, this is your Ng. Here, since it is Ng means delta n naught with respect to, instead of n effective you have delta n naught. Delta n naught means that is the separation of this effective indices of the symmetric and antisymmetric mode. So, I can write this one in brief, that is actually delta Ng. This delta Ng nothing but the group index of the symmetric mode and group index of the asymmetric mode. So, if the symmetric mode and antisymmetric mode, they obviously will have different effective index, no doubt about it. But if I find their group index is somehow identical, almost close, nearby, then delta Ng will be equal to 0. Once it is delta Ng equal to 0, that means I can say that d kappa naught by d lambda equal to 0, that means your kappa naught is wavelength independent. So, I need to find a design where delta Ng is close to 0. Okay. So, details will be found in this IEEE paper, Journal of Light Wave Technology, published in 2017. If you are interested, you can go there. We have discussed detail about how to design a wavelength independent directional coupler. So, let us see how it is done. You take in our hand, what are the parameter for a silicon on insulator waveguide? You have W, you have capital H, that is fixed 220 nanometer, that is the industry standard now. For example, certain most of the semiconductor foundry nowadays, silicon photonics foundry, they are using 220 nanometer. And then another parameter you have, which one? This is H, small h. So, in my hand, I do not have any control over 220, I do not have any control over ND, I do not have any control over NS, I have bit of control over NC, but that is either air or oxide. So, effectively I have the control over WH and of course, S naught. Okay. S naught, as I said, that smaller is better, we will be getting compact. So, that is, let us consider that this S naught is 150 nanometer, which is actually technologically viable, smallest one. More is better, more is not good, you cannot get compact thing. Sometimes you need, for example, you do not need high coupling or something like that, in that time you can use this thing. So, in this case, what we get? We are getting W and H, this is our freedom design parameters. So, what I did, we have used this structure to solve symmetric mode, antisymmetric mode by varying W and small h. And by varying that, we try to find out what is the value of delta Ng. Delta Ng means whatever value I have extracted, this value, this calculation. Okay. So, I calculate symmetric mode, I calculate antisymmetric mode, I calculate their lambda variations, then I know how to calculate this delta Ng, and I plot it here. X axis is the waveguide width and y axis is the small h for a given h value 220 nanometer and lambda around 1550 nanometer initially consider. And in this plane, these are the color profile shows that actually delta Ng value. If I vary, so if I just consider this point, for example, here, that means waveguide width is this much and slab height is this much, this 50 nanometer or above 50 nanometer. So, here whatever the color is there, that color is corresponding to, for example, is somewhere here. So, delta Ng is about minus 0.34. Okay. So, this is how we have mapped, and some value contour plots is given. So, these lines shows that around that any value of W, suppose you want to consider this value. So, this is the waveguide width and this is the slab height. So, there what is the group index, that is minus 0.3, and also same thing will be happening if H is small and I can go to another waveguide width. So, that is how we have calculated. So, this is a kind of lookup map. I can find that suppose I need a certain delta Ng, then I can choose my waveguide width and small h for a given S naught equal to 150 nanometer. And if you see the contour, just look this contour, this is showing 0. That means, if you use any value sitting in this curve, that will give you delta Ng equal to nearly 0. So, that means, for example, if I use some value here, suppose this value I am using here or somewhere here, this value and this value, okay, about 160 and this value, that means delta Ng equal to 0. So, around that, if I design a directional coupler with a gap of 150 nanometer, then I can ensure the directional coupler will be wavelength independent. Okay. So, from this lookup table we can use, because this is standard design. So, we can model accordingly, compact model your device for circuit simulation. So, here it is, here we go. We have just taken 4 different parameters. One is W equal to 550, H, this is actually fixed for all, is 20, and H equal to 100 nanometer. That means, previous picture if you see 550 means around this one, and then what I have 550 and then small h equal to 100 nanometer, small h equal to 100 nanometer. So, here, so this one, this value if I take 550, this one, that is actually DC1. Okay. That means, waveguide width is 550 nanometer and this is 100 nanometer. So, for that purpose, what is our according to the color bar, if you see, that is about somewhere 0.23 or something like that. So, that is called DC1. So, we designed DC1 with this parameter, DC2 another parameter, and DC3 with waveguide width 350 nanometer, slab height 0, DC4 waveguide width 375, 116 things. So, all these 4 parameters if you use, then you see different directional coupler, they will see wavelength dependent delta Ng, how it is varying. Delta Ng for DC1, it is less, relatively less wavelength dependent, but DC3 if you see highly wavelength independent, this delta Ng value. So, delta Ng value highly wavelength dependent means dk lambda by d lambda is also wavelength dependent. So, kappa value will be wavelength dependent. But if you just consider something like DC4, if you all the 4 if you compare, DC4 if you see delta Ng is close to 0, this is the 0 value, this is just crossing close to 0. So, in that case 1525 to 1625, I can expect that if we use these parameters, then that device will be wavelength independent directional coupler. That coupling will be depending on your length, how much length you are using. But for this 150 nanometer gap and waveguide width is 375 nanometer, slab height 60 nanometer, ensuring you that the delta Ng, that means the group index for the symmetric mode and group index for the antisymmetric mode, they are nearly equal, they travel with the same speed. If they travel with the same speed, then you can ensure that obviously that the device is wavelength independent. You check, you see I have taken DC3 and DC4. DC3 is the highly wavelength dependent thing and DC4 is the less wavelength dependent. Now, you see this is the dashed line. So, all the dashed line are corresponding to DC3, that means wavelength dependent, and solid line are wavelength independent. Now, you make a DC of length 4 micron, and if you go for DC3 design, that means dashed one, this design, you see splitting ratio between 2 output ports, that is actually at 1525 it is nearly 50%. As you increase the wavelength, splitting ratio is increasing, it is almost going 90% splitting ratio or something like that. However, if you use DC4, this dimension, you see 1525 also 50%, 1625 also 50%. So, if you are using DC4 and 4 micrometer length, if you use this waveguide design, directional coupler design with S not equal to 150 nanometer and length is exactly 4 micrometer. So, you can get 3 dB power splitting. So, 50% will go to cross port, 50% will go to bar port. So, this design ensures that actually. Now, if you go for same two structure DC3 and DC4 for 8 micron, you see longer length. You see longer length, then it is a 4 is 3 dB. So, double if you do, that will be cross coupling completely. So, you see splitting ratio 1, that means one part will be completely taking up power, one of the port, and other port will be 0. It is a completely cross coupling to the second waveguide. Okay, that is what it is showing, and they are wavelength independent. But other one DC3, you see how they are wavelength dependent, starting from cross coupling, and the other wavelength it is almost 40% coupling ratio. So, that is wavelength dependent. Okay. And even if you go for longer length, then you see it will be more, because that is ultimately cosine square function, sine kappa L, cosine kappa L. So, that will be sinusoidal according to this design. Okay. So, longer length means you can get more dispersion in coupling ratio. Okay. So, just increasing the directional coupler length, you can enhance the dispersion of coupling. However, if you design properly, even longer length also, you see the splitting ratio is fixed. Okay. So, that is how you can engineer your structure to make highly wavelength sensitive kappa or almost nearly wavelength independent kappa. These facts are very, very important if you are designing a broad band for a device or a circuit to operate in wide band, wide optical band. For example, you want to use C band, L band of optical band. So, C band is 1535 to 1565 and L band is 1565 to 1610 and something S band also lower 1525 1500 to 1535 or so. So, entire here we are considering C band and L band, you can get using DC4 design. This is 4 micron if you use 50-50 splitter, 8 micron that means cross coupling, and then if you go for 40 micron 5 times, then again it will go. So, depending on the length actually you get whatever length you use, splitting ratio you can control, but splitting ratio is wavelength independent. But another design if you see just controlling the length, you can actually get more dispersion. So, this different application you can choose this design actually. Fine. So, now I will show some experimental results based on this design, and this type of device fabricated here in IIT Madras using our Nano Center for NEMS and Nanophotonics. You see here, this is a directional coupler, simple directional coupler design. This is 2 by 2, 2 input ports, and this is 2 output ports. You can consider, vice versa you can use also. You see this is GC, GC means grating coupler. Grating coupler means, you know, we have used a vertical grating coupler, so that you can probe, you can use a fiber, bring here, light will be coupled to the waveguide. So, whatever input you want to give, you can just couple here, here also you can couple, and same way you can couple light output side, that we have discussed. From the top you can bring a fiber, bare fiber, and vertically with proper angle you according to your design you bring in, then you can couple light. So, this is the directional coupler you have used, and some directional coupler in the central region, it is not resolved here in this picture. 2 waveguides are coming and they are coupling and they are separating here like this. And in the central portion, if you just zoom in and check how is the 2 waveguide for silicon waveguide looking like, 3D view, it is a little bit tilted sample and SEM image you have taken. And you see the top view, if you see, we wanted to have 360 nanometer dimension and gap is 150 nanometer, and accordingly we are getting in all that. And then if you see that as a function of lambda, when this LDC is 0, just you consider that this bend region coupling, this bend region coupling, and central region nothing is there. That coupling also you can give if you are launching. So, entire power will be in the bar port, cross port almost nothing, 0, right. So, the bend region coupling that gives you light going to cross port and then back again to bar port. So, almost everything you are getting in the bar port, it is designed like that. And then if you are using LDC equal to 5 micron, then you are getting 50-50 according to our theory it says that 4 micron, but experimentally we found that it should be 5 micron actually, because a lot of approximation we have used for modeling purpose, but we can get your fitting parameter accordingly back, and then you get 5 micrometer, you are getting almost 50% cross port and bar port, you see 0.5, 0.5. Red color is for bar port and blue color is for cross port. So, as a function of lambda 1525 to 1625, they are wavelength independent. Now, if your length, directional coupler length increase back again, then you see cross port you are getting completely earlier with LDC equal to 0, bar port you are getting this much and cross port nothing. Here cross port is maximum 1 and bar port 0. So, double the length, that means this is a 3 dB power cut, this is the complete coupling length 10 micrometer. So, here it is shown that as a function of length, you know the coupling in the cross port or bar port, what you say, this is you are getting in the cross port and bar port, right. Bar port, cross port is sine square kappa times L, right. So, this is the LDC. If you just increase L, then coupling, that means it is your T square basically, T square equal to this one, right, sine square kappa L. As you increase, it will be sinusoidally actually you supposed to get. This is the dashed line is the theoretical model, and this is the experimental results you are getting, different length, whatever the power you are getting in the cross port, that actually plotted here. So, that is actually, so if you want that 5 micron, then you are supposed to get 50%. And again, if you just go for around that wavelength 15 micron also, there also you will be getting 50% in the cross port, 50% in the bar port. And if you want to completely switch over, then you go for 10 micron, that is this value. Directional coupler length is 10 micron. So, this is the experimental results, whatever actually proving fine according to our theoretical prediction. Fine. Now, next is I will just discuss a few things that this directional coupler design is not just for power splitter, it can be used for developing different type of circuits. First, I will be just going for different type of devices, from component, directional coupler component to some devices, and then we will go slowly for a circuit for different functionalities. For example, if we have one directional coupler here, another directional coupler here, if you connect them with a waveguide just back to back, then this actually you will launch here, power will be splitted into 2 and it will travel, and then you can interfere there. So, this is actually called 2 by 2 Mach Zehnder, balanced Mach Zehnder interferometer. Balanced why? Because this arm and this arm, they are equal length. So, this type of Mach Zehnder interferometer very important for developing active devices like modulators, and also lot of unitary operations for quantum photonic applications. This Mach Zehnder interferometer very useful, we will be discussing that. And another thing, we can also use unbalanced Mach Zehnder interferometer. Directional coupler, 3 dB directional coupler, 3 dB, this is also 3 dB and this is also 3 dB, and then unbalanced, that means one of the arm longer. So, that type of device also used for different type of band rejection filter, lattice filter design, etc., and sometimes it is called delay line interferometer, DLI. That means one, if you have a signal, one signal, suppose one signal is coming, time dependent signal is, one pulse is coming, then what happens, this pulse will be split into 2 half smaller pulse. Then after traveling here, when they are mixing, at any point you are getting back, then one pulse will be faster, another pulse will be just following. So, you can actually copy one pulse into 2 pulse. So, this type of delay line interferometer it is used also. It is also used for different type of quantum mechanical applications and also microwave photonics, many applications you will see. And you can think of that, okay, you can have some kind of structure, directional coupler, you can design like this micro ring resonator. What is this? Is your bus waveguide you launch here, and because of the coupling, some couple will be there and some wavelength will be dropped here, and that will not be, that will be missing here. So, you can get a filter that is called all pass filter when we will be discussing micro ring resonator. Why it is called all pass we will be discussing, but thing is that certain wavelength will be missing in the transmission. If you just see lambda version, this particular wavelength will be stored here, okay, that is notch filter, and then that is actually all pass filter. This is called micro ring resonator add drop filter. Add drop filter means if you are launching here, that whatever the missing part, that will be stored here, but that can be coupled back here, you can get here that particular wavelength. That particular wavelength will be missing here. So, that means that wavelength is dropped here, and at the same time if you want in this channel back again that wavelength, you can actually couple here and this will come here, come back here. So, it will be adding then. Okay. So, it is, that is why it is called add drop. We will be discussing how the function is there, but what I am saying that you need a directional special type of directional coupler here to design a ring resonator, and you can again this directional coupler together gives you the add drop filters, add drop type multiple ring resonators. Remember that this design is nothing but it is a directional coupler. One of the output port you are giving back to feedback here. It is kind of directional coupler, one port, and another port is here, supposed to be here, and another port supposed to be here. What it is done? This you bend back and couple to the input waveguide. So, that is some kind of feedback. That is how resonator is designed. Okay. And this type of structure, same design, but you can have multiple rings to get a higher order filter, good quality filter, high extinction filter. You can design by coupling rings after rings like this. All these are directional coupler. That means this ring is coupled through this ring again coupled to this ring again coupled to this ring, and finally you can bring as many as ring you want, you can integrate. People have demonstrated up to 235 micro rings like this coupled. They are called coupled ring optical waveguide structures. So, you can get like a drop here, you can launch here, this will be adding port and this will be just pass port. So, you can have 2 by 2 input output ports, right. And also you can just design bit of complicated structure, again very important for quantum mechanical application and filter applications. It is a Mach Zehnder interferometer, first you design, and you use another directional coupler to use integrate one ring here, another directional coupler you integrate another ring, then you can get a complex functions, complex useful functions you will be getting, particularly useful for photon pair source generation, etc. We will be discussing it right by minutes. So, that means what I mean to say that only directional coupler design, that itself can be considered as one of the major building block. Okay. You use this directional coupler to build a versatile different type of passive structure, and that passive structure in future also in course of time you can also make it active, so that you can make also active devices like modulator, switches, all those type of thing you can get, reconfigurable filters, etc. Okay. So, with this I stop here for this lecture today, and next we will be continuing that what is the transfer function of this passive structure. Once you know the transfer function of the directional coupler, then you can actually extract what could be the transfer function for this structure, different structure transfer function we have to derive. That is actually straightforward. Once we start discussing, we will be, and we will try to find out what is the figure of merit of that particular device or circuit when they are operated as a passive component. Okay. Thank you very much.